at the bottom of page 275, it says the fundamental theorem of calculus. If a function f is continuous on the closed interval ab, and f is the antiderivative of f on the interval ab, then you can take the integration and you can just say f of b minus f of a. What does this mean? This means you can take the antiderivative first, the process that you solved for in the first section, and then you can plug in the b and get that answer, and plug in the a and get that answer, and subtract the two, and you will have your area. All right, and so they give you this picture here in your book, and they show the area of the rectangle and the area under the curve. And so basically, you have your change in y and your change in x. And what you're saying is you're finding the area of the whole thing, and you're subtracting out the part you don't need, and you're having what's left over, which is the area of the curve. And so when you go from B to A, you're literally solving the whole thing and subtracting, and you're getting the area of the curve. So let's do some of these. So we have A, B, and C. The first one is x squared minus 3. We are going to take the antiderivative of x squared minus 3. All right? And so this is just a simple antiderivative. We add 1 to the exponent and divide by our new exponent. So for x squared, we should get x cubed over 3, right? Minus 3x. Right? And they note it like this. So we're going to take that from 1 to 2. So we've done the antiderivative. We're going to take that from 1 to 2. All right, so before you would have said 2 minus 1 is 1 over n, right? That would have been my delta x, yes? And then we would have said, then the limit of the summation of I over n, or 1 over n, times I squared over n squared minus 3, right? And we would have done our summation formulas, right? We would have plugged it all in. We would have done the limit as n approaches infinity, and we would have come up with an answer, all right? We are doing the same thing. We are solving for the area under the curve by the first fundamental theorem of calculus, all right? First fundamental of calculus says you don't have to figure out how many rectangles. You don't have to do a number of rectangles as n approaches infinity. You can take the antiderivative, and then you can plug in your top number and subtract it from the plugging in your bottom number. So that's what we're going to do. So we're going to take our 2, and we're going to say 2 cubed over 3 minus 3 times 2. That's plugging in my 2. We are going to subtract what happens when we plug in a 1. And then we're just going to calculate it. What is 2 cubed? 8 thirds minus, this is 6, so that would be what? 18 thirds? I like to get common denominators while I can, right? Minus 1 third minus 9 thirds, yes. All right, so we have 8 minus 18. What does that give us? Negative 10. Minus 1 minus 9 gives us what? Negative 8. Plus, negative 10 plus 8 is negative 2 thirds. All right. Let's do B here. Remember, when you have something like this, you want to rewrite it 3x to the 1/2, right? To make your life a little easier. 1/2, so I'm going to add 1. It'll be 3/2. So I'm going to say divide by 3/2 and multiply by 2 thirds. So I'm going to get rid of that 3 altogether. I'll just have 2x to the 3/2 from 1 to 4. Everybody good with the antiderivative first?
Yes.
Okay. And so when you do this particular one, it's sometimes easier to write it as a square root, just because 4 to the 3/2 seems very weird. But if I were to write this to square root of x cubed, that seems a little more normal, right? Yeah. And so I can take the square root of 4 and cube it, which gives me 8 times 2, which is 16, minus a plug in a 1. Any 1 to any power is just 1, times 2. So my answer here would be 14. All right, antiderivative of secant squared is what?
Oh, wait. Yeah.
There we go. 0 to pi over 4. All right, thank you. Sam's very helpful. So we're going to say the tangent of pi over 4 minus the tangent of 0. Tangent of pi over 4, if you don't remember, is 1, right? Square root of 2 over 2 over square root of 2 over 2. Tangent of 0 is sine over cosine, which is 0 over 1, which is 0. So that's just 1.
Easy.
So this is what it wanted us to find. It said, find the area under the curve of the yx squared plus y equals x squared plus 2 from 0 to 2. We did an infinite number, 0 to 1. We did an infinite number of rectangles is what we did, correct? And so now we're going to do it, first fundamental theorem of calculus. First fundamental theorem of calculus says we can just do 0 to 1 of the x squared plus 2. All right? So we're going to take the antiderivative. What's the antiderivative of x squared?
X cubed over 3.
Antiderivative of 2. From 0 to 1. Okay? We're going to plug in a 1. 1/3 plus 2. Minus, what happens when we plug in a 0? We get 0 plus 0. That's pretty easy. 1/3 plus 2 is 2 1/3, also known as 7 thirds. Absolute value. So with absolute value, you have to consider the fact that there are two parts to this thing. It's when it flips places here. And so it is always going to be positive, and so you have to consider from 0 to 2 if anything makes it negative, okay? If anything makes it negative, then you have to do the opposite of that guy. And so for an absolute value, the first thing you want to do is you want to set him equal to 0 and say, well, at x equals 1/2, I have a change, right? And if I put something in less than 1/2, so if I put a 0 in, this guy's going to be negative. So from 0 to 1/2, I am going to yield a negative answer in just 2x minus 1, correct? And then from 1/2 to 2, I'm going to yield a positive answer. And so anytime you're going to yield a negative answer, you have to negate that antiderivative. So I would have to actually set up 2. I would have to say from 0 to 1/2, I'm going to do the opposite of this guy. And I'm going to add that from 1/2 to 2 with how it is normally because it's not affected. So I have to set up 2 of those. Make sense? So you'll notice we have this little section here from 0 to 1/2. We have to add that to this section here from 1/2 to 2. All right? Absolute. So we're basically just taking the antiderivative of 2x minus 1, right? But from 0 to 1/2, 2x minus 1 would normally be negative, but it's absolute value. So we're just putting this negative in front of it so that we're changing all those negatives to positives. This is the way we're saying this is always going to be positive. We're finding the area, and it's always going to be positive. And so we're not using, the absolute value is just, for our knowledge, we're actually differentiating the 2x minus 1. Antiderivative is much the same. We just have a negative in front of it. So the antiderivative of this first piece is 2x squared over 2. So it's going to be x squared. And then I'm going to have to put that negative there. 1 is just going to be just x. But if I distribute that negative, it's going to be plus. And I'm going to do that from 0 to 1/2. For this guy, it's going to be, this is a minus, that's a minus. It's going to just be the same thing, except it's going to be positive x squared minus x from 1/2 to 2. Right? So these are just going to be opposites of each other. They always will be. And then you have to do them individually. So I have to actually do negative 1/4, that's 1/2 squared, plus 1/2, minus, of course, 0. That's my first step. Plus, I have to do 4 minus 2, minus 1/4, minus 1/2. That's my second set. So far, so good?
Yeah.
All right, so then get a common denominator here, negative 1/2 plus 2/4 gives me just positive 1/4, negative 1/4.
Where did the minus 0 come from?
When I plugged this guy in.
Oh, okay.
I just showed it. Obviously, 0 is important when it's a top number because it actually will change your negative. When it's a bottom number, it's just subtracting 0. For here, I have 2, and this actually becomes negative 1/4, so 2 minus 1/4, right, would be 2 1/4, which is what, 2 1/2, 5/2 would be your answer there. Where it's basically a polynomial. They want us to go from 0 to 2. And you really just, I mean, in this case, my 0 is on the bottom, so it's actually not going to make a difference. But so I have this right here. You could break them up all from 0 to 2. I don't. All right. You could do the 2x squared from 0 to 2, the negative 3x from 0 to 2, and the 2 from 0 to 2. I don't do that. I actually do the whole thing and plug in my 2, subtract, plug in my 0, or whatever number I have. So I do them all together. So this would be x cubed over 3 minus x squared over 2 plus 2x for my antiderivative, and I would do all of that from 0 to 2. You could do them individually. Again, it doesn't matter. So I get, what, 16 cubed over 3 minus... Yes. I said it, and I didn't write it. Sorry. That would be 12 over 2 plus 4. When you subtract, so this is the 2 minus what happens when you plug in a 0. I always write that because I don't want you to forget if it wasn't a 0 there, you do need to plug it in.
So if the 0 is on the top, you don't need to subtract it.
You would. That's why I write it, because had it been like negative 2 to 0, it would have been 0 minus this answer, which does change your negative, positive, negative.
Okay.
But I always write it there so you don't forget that it is a 2-part problem in case you're not going from 0 to 2. And then you can either get a common denominator here, or you can just do a mixed number, whatever, however you like to do it. It doesn't matter to me, but this is going to be 6, right? So it's going to be 16 thirds minus 2 or minus 6 thirds. So we're going to get 10 thirds there. For derivatives, we did mean value versus instantaneous. And so mean value would be the whole amount over, so it's basically your slope formula, right? F of b minus f of a over b minus a. And so when you're doing integration, it's similar. You do have that b minus a. And so they have f of c, which is the antiderivative of, and then times b minus a for the mean value theorem. And what it actually does is you can find the average value of a function using this definition down here, which is also, I think, on page, where is it? And so mean value leads us to average value of a function. And so if you want to find the average value of a function, what you'll see here is we have this curve, and if we were finding the area under the curve, we would actually do my definite integration here. Average value kind of makes it into what would be a standard geometric shape. And we're saying this is our average. We kind of cut through it and down and find the average value of it. And so to find the average value, you use this b minus a, but you use it with a reciprocal here. So we say 1 over b minus a times the definite integration, and that will give us our average value of the function over a specific interval. All right, and so average value comes from the mean value theorem. And mean value is just that if it's continuous, there's a number c such that that specific number will allow us to solve. And so somewhere in between a and b, we're going to find that c that gives us the actual average, just like we did on instantaneous versus average velocity or something like that. There is a number that exists that gives us the exact instantaneous if that is the average. And that's kind of what how those two go hand in hand. So let's look at the example, finding the average value. It says find the average value, and they give us the function 3x squared minus 2x, and they want us to do it on the interval 1, 4. 1, 4. So they don't want the actual number here of the definite integration. They want the average value. And so we're going to use that 1 over b minus a from a to b of the function. And so we're going to set it up. We're going to say 1 over, and b minus a is going to be 4 minus 1. And we're going to do that times the integration from 1 to 4 of the function that we have been given. All right. And so what you can do, because that's a kind of a coefficient, the 1/3 is a coefficient of it, you can do the derivative and do the 1/3 at the end, basically. And so I would actually leave this 1/3 alone, and I would do this integration here. So x cubed over 3 times 3, of course, is just going to be x cubed, and x squared over 2 times the 2 is just going to be x squared from 1 to 4. And I will do that integration, and then I'll multiply it by the 1/3. And so we'll plug in the 4. We'll get, what, 64 minus 16 minus, what, when I plug in a 1, I get 0. Right. And then I'm going to get, what, 48, 1/3 times 48, which is going to give me 16. So if I were to do the average value here, the average value then would be 16, average value of the function. All right, so when we look at the second fundamental theorem of calculus, it seems daunting, but it's not. All right, so at this point, we've gone from constant to constant, like a to b. Those are both numbers, constants. And so then you can have an integration that goes from a constant to a function of x. All right. And so when you do this, they typically use this when you're taking the derivative of an antiderivative. And so when you do something like this, so they give you the example right here from 0 to x of the cosine t dt, and then they give you certain x's. And they just go and they plug in sine of x minus sine of 0, and they just plug it in and they plug them all in. But when you're doing this, it literally is just plugging in the function once you take the antiderivative. So if I were to take the antiderivative, I would plug in an x as my top and subtract the constant from the back end, and I would have a new function, all right? And so the second fundamental theorem of calculus actually deals with taking the derivative of an antiderivative. So the second fundamental theorem of calculus says if f is continuous on an open interval I containing a, then for every x in the interval, the derivative d of dx of the function 0 or a to x, a being a constant, is just going to be f of x. And if it's something other than x, you have to consider the derivative of the function. And so we're going to do 1 from 0 to x, and 1 from 0 are a number to the function of x that's not just x. But what you do here is, if this is x, we don't have a problem because the derivative of x is just 1. So it's like times, oh, where'd you go? Come back. Times the derivative of x, which is just 1. But if it's something other than x, you have to consider the fact that you have to take the derivative of x. Now, think about it this way. You are taking the derivative of an antiderivative. They cancel each other out, and you're left with just the function, okay? Like if I were to multiply by 5 and divide by 5, well, I'm left with whatever I was multiplying by. 5 times x divided by 5 is just x, right? So they cancel each other out. So the derivative and the antiderivative cancel each other out. But when you have a function as your top bound or your upper bound, you also have to consider the derivative of the function itself, okay? So let's look at these examples. So if you look at it on, and we'll do 2 of them, all right? So I'm actually going to jump to example 7. All right. So if I look at this, what it's telling me to do here, I am just going to say, well, if I take the derivative of the antiderivative, it should cancel each other out, and I'm just left with what's in the middle. But I want it of x, not of t. And so I'm left with just the square root. And instead of the t here, I'm going to plug in an x squared plus 1, right? And that would be my derivative of my antiderivative. Derivative of the antiderivative. They cancel each other out. All right? So all I did was I took the derivative of the antiderivative. You don't need to actually do it. If you do the antiderivative and then you take the derivative, you're going to work back to where you got started from. All right? What you do have to consider is they want it for x. And so you do have to plug the x in for the t. Very simple. That's very easy when it's just an x, because considering the derivative of x is just 1, it doesn't affect anything else, all right? It's really just as easy when you have something other than x there. So look at the next example. They want the derivative of the antiderivative, okay? Derivative of the antiderivative. Well, if I did it, the antiderivative of cosine is just sine. And then if I take that derivative, it would be cosine, right? And so I know I just get what's in there. I get cosine. Instead of t, I want my top bound here, which is x cubed. Cosine of x cubed. And in this case, I have to consider the derivative of x cubed. Okay, so it's think of it almost like the chain rule. I have to multiply by my derivative of x cubed, which is 3x squared. So my final answer, you typically want to put this guy in front. So I would say 3x squared cosine of x cubed. So second fundamental theorem of calculus just says, if I have a function as my upper bound, and I'm taking the derivative of the antiderivative, I have to consider the derivative of my upper bound when I do it. I would have 1 over, and instead of t cubed, I would have x squared cubed, and I would multiply that by the derivative of x squared, which is 2x. So I would 2x over x to the 6th. You can reduce that to 2 over x to the 5th.